5, 6, 7, 8, 9. I think it's a 9-digit lottery. And his father said, "You're crazy, this number's never going to come." It's just like saying, you know, give me a random sequence. This is a random sequence, right? So how do you know when you make a probable inference that in fact something's wrong with the dice? It turned out, oh wow, 10 times in a row. Is it good enough to say, throw the dice away, this dice is not good? 100 times in a row? 1,000 times in a row? 1,000,000 times in a row? No. So you need to think about this. So what we do is we build a little Markov model for the casino. The casino has only 2 states. A state with fair dice and a state with loaded dice. It transitions between these states with a certain probability. It stays in that state with a very high probability, say 1 minus epsilon, where epsilon is quite small. And every now and then, rarely, because it doesn't want to really offend customers too much, shifts just enough, does it just enough to make a profit, right? It shifts to a state with loaded dice. Again, it doesn't stay in that state too much. So there's some delta here. And with a fairly high probability, we'll return to a fair state. Okay? And then in the fair state, the probability of the 1 is the same as the 2. So there's an emission or production function. It's often called emission. The state emits a value. Chooses it at random from 6 possible values. And in this case, of course, all 6 choices are equally likely. It's a fair die. In the loaded case, maybe P1 is a bit higher. P6 is a bit lower. Okay? Something like that. Depends on the physics and what they're really doing to this die, so I don't know. But it's no longer a uniform distribution among the 6 values. And this is the whole system. Now, there's a number of questions you can ask about this. First is, if you were to go to the casino, you might even be told by the manager what is epsilon, what is delta, and what is the probability distribution of the loaded dice. Because as I said, the casinos don't make any mystery of the fact that they are there to make money, and they do not play exactly fair odds. So they can tell you this. It doesn't hurt them, because you can't really tell when they switch dice anyway. Suppose you knew the value. Suppose you know this epsilon, you know this delta, and you know the probability distribution of the loaded dice. Now, can we decide what state the casino is in? And each step. This is what's called a hidden Markov model. We can observe the output, we do not know the states. Okay? We can see what the result of throwing the dice is every time. We know all the values of the dice. The throwers gave us these values, but we do not know whether this throw, that throw, this throw, that throw, whether the casino was in a fair state by using fair dice, or was in an unfair loaded state for the dice. Okay? And somewhere transitions occur, and we would like to reconstruct a plausible history of fair and loaded. Deciding that maybe here is a change occurred, and we move from a fair state to a loaded state. What does this?